Did you know that when you bring a light harvesting complex close to a metallic nanoparticle, like a gold nanorod, the spectroscopic properties of the light harvesting complex can be drastically tuned? I find this very intriguing, and one of my PhD students, Farouk Cheyune, has investigated this phenomenon experimentally, while another PhD student and postdoc, Luke Ugwoke, has developed some analytical models to explore what is actually going on. Okay, so nanorods are extremely nice systems to work with because firstly, they are relatively cheap to make, and secondly, you can significantly shift their absorption and emission spectra along the wavelength scale by simply changing the length of the nanorods. So we use a relatively simple but very cost-efficient method to synthesize gold nanorods. And we made the dimensions of the nanorods such that the absorption band of the longitudinal plasmon mode overlaps strongly with the absorption and fluorescence spectra of LHC2 to ensure optimal interaction between them. And then we immobilized the gold nanorods, and on top of that, or actually between them, LHC2 complexes using a layer-by-layer spin-assisted method, also a relatively simple but very economical method. And this was done to investigate the distance-dependent interactions between a single nanorod and a single LHC2 complex. So let me zoom in here a little bit. Let's see. Okay, there we go. Right, so when LHC2 gets very close to a gold nanorod, so actually when it gets in or near the plasmonic hotspot at the tip of a gold nanorod, the fluorescence gets enhanced by up to 2 orders of magnitude. So here are two examples of isolated LH2 complexes measured one at a time. You see the typical blinking behavior, which is a good sign that this is a single LH2 complex, actually a single quantum unit, the fusion limited system. Okay, so here are isolated LHC2 and LHC2 that was in the plasmonic hotspot of a gold nanorod. So here's one example, another example, and they still exhibit the one-step blinking behavior. So reversible reductions in the fluorescence intensity, and eventually, after enough excitation de-excitation cycles, you get photo bleaching. Okay, so this is also a sign that this was a single LH2 complex that interacted strongly with a plasmonic nanoparticle. Right, so here you can also see the enhancement factor. So this was the fluorescence enhancement factor, which, so we got values of a few hundred, and this was accompanied by a very strong reduction in the fluorescence lifetime. So isolated LHC2 has a fluorescence lifetime of between 3 and 4 nanoseconds. And when you put it in a plasmonic hotspot of a gold nanorod, then this lifetime is reduced by up to about 100 times. So tens of picosecond lifetimes is what one gets. Okay, so in other words, what we get here is that both the radiative rate and the non-radiative rate are significantly altered due to the interaction of the plasmonic field with the light harvesting complex. And then the fluorescence enhancement, that is a product of emission enhancement and excitation enhancement. And these enhancement factors depend on nanoparticle size, the distance between LHC2 and the gold nanorod, and so on. So all these factors can be precisely controlled. So in other words, this method gives one a handle to actively tune both the radiative and the non-radiative rate. So obviously the two are not completely independent. So you can see here that it seems like there's some inverse relationship between the radiative and the non-radiative rates. But in order to understand exactly what's going on, we have to do some modeling. And that is what we are doing here. So let's first have a look at the simulation of the excitation field. So a gold nanorod concentrates the incident light in hot spots close to the surface. And what makes the nanorod pretty useful is that it exhibits a so-called lightning rod effect, whereby it concentrates the light very intensely at its tips, specifically, due to the high density of surface charges at those regions. Now, as you bring a light harvesting complex like LHC2, this is what was simulated here, an LHC2 complex, if you bring it closer to the metallic surface, the excitation rate dramatically increases. And it will increase until it reaches until there's a zero distance between the two. But obviously, this is not the only effect. This is only the excitation field. So we also have to look at the emission field, emission enhancement, which is shown here. Okay, so for that purpose, we have developed analytical models, and one can approach this classically, so pure classical model, or one could look at a classical plexitonic model, where plexitonic stands for the plasmon-exciton interaction. So this, in that case, such a type of model is a semi-classical model, or one could look at a pure quantum model, which we have also started to develop here. So one could call this a quantum plexitonic picture. Okay, so let's first have a look at the classical picture. So this is a relatively simple model, but obviously, since it's an analytical model, one needs a few approximations. But now, in order to make a better comparison with experimental results, in other words, to have a reliable model, we also implemented a number of dynamical corrections. Okay, so here's our model, the nanorod here, and we are modeling LHC2 by a dipole antenna, or a molecular point dipole. And then we can consider dipole-dipole interaction between LHC2 and the gold nanoparticle. So now in the weak excitation limit, both the excitation rate and the emission rate are multiplied by an enhancement factor. So you can see here in the blocks, the enhancement factor for the excitation rate, the enhancement factor for the emission rate is called the Purcell factor, which is written here. And this is dependent on the dipole moment of LHC2 and the dipole moment that's induced by the plasmon field is the other parameter there. Okay, so these are two rates that we have to add, or actually two enhancement factors, and then we have to add another rate. So another non-radiative decay channel. So this is called gamma absorption, which represents energy transfer from LHC2 to the metallic nanoparticle. So all these plasmon-induced changes in the rates depend strongly on the distance between LHC2 and the nanoparticle surface, but gamma absorption dominates at small distances, as you can see here. So there's a strong increase in the quantum yield, the effective quantum yield, but then as the separation between LHC2 and the gold nanoparticle gets small, so as LHC2 gets closer to the nanoparticle surface, the quantum yield drops significantly until it reaches zero when LHC2 touches the nanoparticle surface. Okay, and this is because of the thermal dissipation rate, this gamma absorption that starts to dominate at very short distances. Okay, so putting all these contributions together gives us the distance-dependent and wavelength-dependent fluorescence enhancements. This classical model with all the corrections that we have added already gives a pretty good comparison with the experimental results. And yeah, we can go into more detail if you're interested in that. So just a couple of words about the quantum picture. So I'm not going to explain all of this now. If you're interested, we can go into more details there. But the most important result here is that the quantum approach predicts even stronger fluorescence enhancement factors than the classical approach up there. So there's obviously a lot more detail and complexity in these models, and I would love to discuss all of this with you, and of course also discuss the exciting experimental results with you. So I hope to see you soon.